Oh, okay. So what time should this end?
You have 25 minutes.
Okay. Okay, thank you. Good. Okay, sorry. So thank you again. Thank you for coming. Thank you for letting me speak. And as he mentioned, I'll speak about the average size of two Selmer groups of elliptic curves over function fields. And by the way, the slides are available on my website /slides if you're interested. Okay, so this talk, it's really an algebraic geometry talk. I want to talk about moduli of curves, but I'll apply them to understanding a problem in number theory. So for the first half, I want to describe the number theory problem, and then I want to describe how to use moduli of curves to attack it. So here's a motivating question from number theory. Take an elliptic curve. Okay, so here, take an elliptic curve over a global field. Just pretend the field is FQ adjoin T, a finite field adjoin a variable. And a classic theorem, Mordell-Weil, says the group of rational points is a finitely generated abelian group. In other words, you can write these rational points as z to a power plus a torsion, finite torsion group, and that power is called the rank of the elliptic curve. And the motivating question is, how big is the rank of an average elliptic curve? Okay, so to answer this question, we'll look at some moduli spaces of curves and moduli spaces of elliptic surfaces. But first, let me describe my approach to how we'll sort of get at the rank of the curve. So in order to get at the rank of the curve, we'll bound it by something called a Selmer group. So let me define a Selmer group. So I'll work over a function field, so FQ adjoin T, and I'll let V denote closed points of P1. So in number theory, they call these places of K. And from the, so if you take an elliptic curve and you look at multiplication by 2, there's an exact sequence. E of 2 torsion goes to E by multiplication by 2. And this induces an exact sequence on étale cohomology. So E mod twice the K points mod twice the K points, that's from H0 to H1 of E of 2 to H1 of E. And you can take this exact sequence and restrict it to all the places. And so you get the same exact sequence for each closed point of P1, and you take the product. And the definition of the two-Selmer group, which will help us get a bound for the rank, is it's the kernel of this diagonal map alpha. So this seems a bit opaque maybe, but geometrically you can think of this as taking this H1 of K, this is E of 2 torsors for K. So it's like a degree 4 scheme over K with a 2 torsion action, and you're asking some trivial condition at all closed points. So it's sort of saying this 2 torsion torsor spreads out to something over P1. Okay, so that's the two-Selmer group, and the Tate-Schaff-Rabitz group is an analogously defined object for the elliptic curve. So it's like torsors for the elliptic curve with some local restriction. Okay, so here's how we use the Selmer groups to bound the rank. So there's an elementary exact sequence you get. It goes from the K points mod twice the K points to the two-Selmer group, and then to this 2 torsion in the Tate-Schaff-Rabitz group. And the proof is just a straightforward diagram chase. So the 2 torsion in the Tate-Schaff-Rabitz group, if you go back a slide, you can just, from the definition, it's the kernel of this map beta. And so what I'm saying is there's an exact sequence from this to the kernel of alpha to the kernel of beta, and that's just a diagram chase. Okay, so you have this exact sequence, and let me point out how this, so we're going to try to bound the two-Selmer group, and I just want to explain why bounding the two-Selmer group bounds the rank. So the point is just, if the E of K, remember the rank is just what E of K, it's the free part of E of K, Z to what power. So if, say the rank is, you have some rank, then if you take E of K, if it's Z to the R, E of K is Z to the R, then E of K mod 2 E of K is Z mod 2 to the R. So the rank will be encapsulated by this term. This will be a bound for the rank, and then it'll inject into the two-Selmer group. So if we can bound the two-Selmer group, we can bound the rank. Okay. So now I want to talk about bounding the two-Selmer group, and how to bound it. Well, in order to bound it, I need to tell you how to count, because the problem is we want to find the average size of the two-Selmer group, but there are infinitely many elliptic curves. So we have to say, how are you going to count average size over an infinite set? And the point is that you can define something called discriminant, and we'll count up to a given discriminant, and then we'll take a limit. So if you take an elliptic curve, let's say characteristic not 2 or 3, so over a field of characteristic more than 3, you can always write it in this form, in this Weierstrass form, where, so here A and B are two polynomials, because they're elements in the function field, so a priori they're rational functions, but you can actually write them as polynomials, and their degrees will have to be 4D and 6D as homogeneous polynomials. And then the discriminant is just the discriminant of the elliptic curve is just the discriminant of this cubic equation, and it's basically a cubed plus b squared. And so we'll count up to a certain height. The height is just the degree of the discriminant. So if a has degree 4D, then a cubed has degree 12D. So the degree of the discriminant will always be a multiple of 12. And to define the average size, we'll just count all curves up to a given discriminant. So we'll take what you think it should be. You look at all curves up to a given height, and you add the size of the two-Selmer group, and then just divide by the number of curves. And then you take the limit as the height goes to infinity. So that's how we'll count them, just by this height measure. And the theorem is, so we want to understand the average rank, so we want to understand the average size of the Selmer group. The theorem is the average size of the Selmer group is 3, up to some small error term. So I just want to make a few remarks about what's been proven before, but any questions so far before I continue? Okay, so let me give some remarks about what's been proven before. So this result for the two Selmer groups over function fields was actually already proven. It was proven by Ho, Lei Hung, and Go a few years ago, around 2014. And they had a different proof idea, so I'll talk about one proof idea, but they had another interesting proof idea, which is to count this average size by realizing Selmer elements as maps from P1 or some curve to a certain stack. And P1 points of the stack or curve points of the stack were the same as two Selmer elements. And this was an interesting stack. It's not separated. It is Lee Mumford. Anyway, there's other results. So if instead of working over function fields, you work over number fields, in particular over Q, Bhargava and Shankar computed this. And they also computed the average size of 3, 4, and 5 Selmer groups. And a version for 3 Selmer groups was proven by Johan de Jong around 2000. An analogous story, but there the average size is 4 instead of 3. And now I want to discuss a proof I came up with using the geometry of curves and modular spaces of curves. Okay, so just before I get to my proof, I want to make one remark just to see how this average size of the two Selmer group implies, so the theorem is that the average size is about 3. I want to say why this implies that the average size, the average rank of an elliptic curve is at most 3/2. Okay, so the reason is a very elementary inequality. 2 to some integer, some non-negative integer, is always at least 2 times the integer, right? Because 2 to the 1 is at least 2, 2 to the 2 is 4, and then 2 to the 3 is 8, which is more than 2 times 3. So this is just a true fact about integers, non-negative integers. Okay, so then granting this fact, we have by this theorem that 3 is about the average size. This is the size, and we want to relate that to the rank. But by this inequality, it's more than 2 times the rank. And then by that exact sequence a few slides before, this rank bounds the rank of the two Selmer group bounds the rank of E. So you get 3 is more than twice the rank of E, and when you divide by 2, you get 3/2 is more than the average rank. Okay, so that's why this size of the two Selmer group relates to the rank. Okay, so now let me move to the algebraic geometry side and discuss the proof. Okay, so I'm going to relate, so we have to count the average size of two Selmer groups, and I want to relate, so there's 2 parts. There's the two Selmer groups and there's the number of elliptic curves. So I'll relate 2 Selmer groups to degree 4 covers of P1 and counting these elliptic curves to degree 3 covers of P1. So let me do that now. So we'll start with the simpler case, which is the elliptic curves. So let me just recall, a Hirzebruch surface is the Fn, I'll denote it, is just proj of O plus O of n. So this is a P1 bundle over P1, and all P1 bundles over P1 are one of these. And so the first lemma I want to explain is there's a bijection between elliptic curves, which is one of these things we're trying to count. Elliptic curves over a function field, and embeddings from a degree 3 cover union of P1 into a Hirzebruch surface. So let's see why that is. So here's the proof idea. So we want to start with an elliptic curve over a function field and get out a degree 3 cover of P1 inside a Hirzebruch surface, not meeting a copy of P1. So start with our elliptic curve over a function field, and then spread it out to something over P1. So you can take the minimal proper regular model, which is a surface, which is in this case, a smooth proper surface over P1 over FQ, which is minimal in a certain sense. And when you spread it out to this, you also, in this elliptic curve, you have the two torsion. So there's the identity section, there's the identity point of the elliptic curve, and there's a degree 3 non-trivial two torsion scheme. And when you spread it out, this degree 3 scheme becomes a degree 3 cover of P1, and the identity section becomes a copy of P1. Okay, so let's keep going. So we've just taken our elliptic curve and we've spread it out to a minimal proper regular model. And now the hyperelliptic involution on the elliptic curve, which is multiplication by -1, spreads out to a hyperelliptic involution on the minimal proper regular model. And so you can quotient by that. And when you quotient by that, you get a Hirzebruch surface. Basically because, so if you take an elliptic curve and you quotient by the hyperelliptic involution, you get a P1. And then that's telling you that all the fibers of this surface should be P1, so it's some Hirzebruch surface. And inside of it, you can look at the ramification locus of this map, and that's exactly the two torsion of the elliptic curve, which is, or the image of that, which is this degree 3 curve together with a copy of P1. So we started with elliptic curve over the function field, and from it we got this elliptic surface, and then we quotiented and we got this degree 3 curve. Okay, so this is how the bijection goes from elliptic curves over function fields to trigonal curves, that not meeting this copy of P1. And conversely, if you started with this trigonal curve, you could take the double cover branched over this and get the elliptic surface, and then take the generic fiber and get the elliptic curve. Okay, so that's what we just showed. There's a bijection between elliptic curves over function fields and trigonal curves not meeting a P1 inside a Hirzebruch surface. So now I want to address the two Selmer element. So that sort of addresses the elliptic curves, the sort of trivial two Selmer elements. So what about these two Selmer elements? So there's an analogous lemma here. There's a bijection between two Selmer elements and over a function field, and embeddings of a degree 4 curve over P1 into a Hirzebruch surface. So, and the proof is going to be almost the same as the previous proof. But just as a remark, because it was in the abstract, I'll just say that, so now we have these two lemmas which are giving sort of, on the one hand, bijections between elliptic curves and degree 3 curves, and bijections between two Selmer elements and degree 4 curves. And the degree 4 curves are actually related to the degree 3 curves by a very classical story called the Riccias correspondence. And essentially the degree 3 curve, if you know about solving the quartic equation, the degree 3 curve is like the resolvent cubic of this degree 4 curve over the generic fiber. Okay, but let me address this lemma. So why is there this sort of bijection between degree 4 curves and two Selmer elements? So again, it's a similar story. We start with our two Selmer element. But what's a two Selmer element? So I defined it quickly at the beginning, but it's basically some torsor for the two torsion of E with some conditions. And so it will map into a genus 1 curve, canonically, and so you can realize this torsor for the two torsion has some degree 4 scheme Z inside a genus 1 curve Y. But not an elliptic curve, I don't have a point, just a genus 1 curve. But analogously, you can still spread this out to a minimal proper regular model, works for any curve. So you have now this minimal proper regular model, which is a genus 1 surface over P1. And again, you spread out this torsor for the two torsion, so it spreads out now into a degree 4 curve. All right, and now we do the same thing. So we have again, we spread out our elliptic curve over the function field into an elliptic surface, or a genus 1 surface over P1, and we still have this hyperelliptic involution which fixes the degree 4 curve. And so we can quotient by that, and again, for the same reason, we get a Hirzebruch surface, and the ramification locus is this degree 4 curve. So again, we started with some two Selmer element, and we produced from it a tetragonal curve, a degree 4 curve inside a Hirzebruch surface. And conversely, you can go back by taking the double cover branched over this double cover of the Hirzebruch surface branched over this degree 4 curve, and then taking the generic fiber. Okay, so far, we sort of gave some bijections between two Selmer elements and geometric spaces. And we want to count how many of them, what's the ratio of these two Selmer elements to elliptic curves. And so in order to count them, I just need a quick lemma that tells me how to count them. And then we'll be able to prove the theorem. So what this lemma says is, if you look at degree 4 curves inside Hirzebruch surfaces, there's 3 types of them. So the first type is sort of the trivial type, which is coming from these degree 3 curves union at P1. So these are the disconnected type. So if the curve is disconnected, it will always be sort of, or most of the time, be a degree 3 curve union a copy of P1. And further, all of these lie in a particular linear system on a particular Hirzebruch surface. So the other 2 types, the connected types, those will either lie in a general member will either lie in F0, so that's P1 times P1, or it'll lie on F1, which is P2 blown up at a point. And again, these 2 types are also in particular linear systems. And any smooth member of these linear systems will do. And the amazing fact is, these 3 types all have the same dimension. After Cauchy by automorphisms, the dimensions of these linear systems are all the same. So this is sort of where our 3 is coming from. The average size 3 is coming from sort of these 3 linear systems, all of the same dimension. Okay, so let me just explain why all this proves the theorem. So I want to prove that the average size of the 2 Selmer group is 3. Okay, so just what's the definition? The average size of the 2 Selmer group is this limit in the discriminant of the ratio of the number of 2 Selmer elements to the number of elliptic curves over the function field. But we have those 2 lemmas that basically address the numerator and denominator. So remember, the denominator, this is just the number of elliptic curves over a function field. And we had that bijection between elliptic curves and degree 3 curves. So that's just the number of degree 3 curves inside Hirzebruch surfaces, not meaning P1. And the numerator, we said, was degree 4 curves. That was the other lemma. And that's just the number of degree 4 curves in a Hirzebruch surface, right? But then by that previous slide right here, this slide, we know how to count these. So this top has 3 components. So it's 3 times some linear system, which is q to some power. That's how many elements are in the linear system. And the denominator is just the number of trigonal curves, which was also one of these 3 linear systems from the previous slide. And so the ratio is just about 3, because there were 3 linear systems and 1 was these trivial elements. Okay, so that's the idea of the proof. Any questions so far? Okay. So I just want to, in the last couple of minutes, say a little bit about some related questions. So this was 2 Selmer groups, but a natural question is, well, what if instead of looking at 2 Selmer groups, you look at higher Selmer groups? Look at 3 or 4 or higher. And there's a nice conjecture about what the average size should be. So by Bhargava and Shankar, they predict that the average size of the Selmer group for the n Selmer group should be the sum of the divisors of n. So for 2, that checks out, because the sum of divisors of 2 is 1 plus 2, which is 3, which is the average size. And in fact, they've proven this for n up to 5. And so this is their conjecture. And let me try to give a geometric interpretation, possible way to sort of address their conjecture. So geometrically, let's understand what we did in this proof. So the 3 had a geometric reason. It wasn't just random. There were actually three linear systems in the picture. And the first one was sort of trivial elements, so that's where this 1 is coming from. And then there were 2 more components. And the 2 components corresponded to curves in linear systems on certain Hirzebruch surfaces, which are associated to vector bundles on P1. And there were moduli of curves on these Hirzebruch surfaces. So I just want to mention these particular, in the simplest case, which is this height, this discriminant degree is 12, Vakil had some identified these moduli spaces. So the curves on O plus O were corresponding, sorry, the 2 Selmer elements which corresponded to curves on O plus O were parametrizing maps from hyperelliptic curves of genus 3. And the two Selmer elements on O plus O of 1, another component, are the same as maps given by a subsystem of the canonical linear system. So there's a lot of geometry here. And I just want to summarize, I want to summarize sort of what's known about different spaces. So remember here we have these geometric descriptions, and you might guess there's a geometric description for arbitrary Selmer spaces. And in fact, you can sort of parameterize Selmer groups as points on certain moduli spaces. And I won't say how to construct it because there's not much time, but for each n, so you can look at the n Selmer group of sort of height d elliptic surfaces. And for each n and d, there's a moduli space. So you can imagine each of these squares in the grid, there's a moduli space. And what parts of these moduli spaces have been investigated? So the simplest case is these one Selmer elements are the same as elliptic surfaces. And so, okay, a lot of people study those. And then, as I mentioned, Ravi studied this particular case of sort of height 1 and 2 Selmer elements. And then in this talk, we were talking about the average size of the 2 Selmer group, which is what happens as you sort of go along this row and let the height go to infinity. We're taking this limit. Okay, but there's some more things people have studied. So as I mentioned when I stated this theorem, Johan de Jong studied the average size of the 3 Selmer group, which is sort of going along this row. And another interesting direction to look in is going vertically. So remember, maybe you know, degree 1 elliptic surfaces, or height 1, are the same as del Pezzo 1 surfaces. Height 2 are the same as K3 elliptic surfaces. So if you sort of go vertically, these Selmer spaces actually tell you about configurations of lines on del Pezzo surfaces, del Pezzo degree 1 surfaces. Okay. And the last direction I want to just mention is, so you could continue this pattern of going horizontally, and you could ask what's the average size of the n Selmer group. So this is what I was talking about, this conjecture of Bhargava and Shankar. And they predict that the average size is the number of divisors of n. And so if you think about this question, you're sort of trying to count the number of FQ points on these certain varieties parameterizing these Selmer elements. And you can phrase it, you might be familiar with, there's sort of a way to phrase this using Lefschetz, Grothendieck-Lefschetz formula in terms of homological stability. So if you can show the homologies of these moduli spaces stabilize, then you can use this to count the number of FQ points and then determine the average size of these Selmer groups. So this is something I've been thinking about more recently and thinking about how to compute. Maybe the first case is just seeing that H0 stabilizes, that the number of these components stabilize. So I think there's a lot of interesting directions to look at these moduli spaces. And thank you so much for your time.